So I talked about water moving as sheets. It causes rapid erosion of the continents, and the deposition forms the continental shelves. Now I'm going to talk about the third part of this. It's called planation surfaces. What in the world is a planation surface? Well, think of plane. That can give you a hint. Plane. Well, here's what the Dictionary of Geological Terms says. It's a land surface shaped and subdued by the action of erosion. Well, okay. Especially by running water. Well, why running water? Well, it's kind of interesting. You have those rounded rocks on top of these plane surfaces. Rounded rocks are rounded primarily, in fact, totally by erosion. There are a few ways you can weather rounded rocks, but not when you see millions of them on here. They're not by weathering. They're by running water. The term is generally applied to a level or nearly level surface. If it's really flat, you call it a planation surface. If it's kind of rolling surface like this, you'd be called an erosion surface. That's the difference. I'm going to say planation surface because many of these surfaces are very flat looking. I'm going to show you. Here's an example of a planation surface, a small one. This is a little erosional remnant in the Bighorn Basin near Graybull, Wyoming. The sediments were probably a couple thousand feet deep at one time in the Bighorn Basin and eroded down to that level during the sheet flow erosion. And so this little remnant here was left. Here's the sedimentary rocks, which are those layer cake rocks you see when you drive around, especially in the Rocky Mountains. But you can see the sediments are dipping to the east about 25 degrees, and they're a combination of hard sandstones and soft shales dipping in that direction. But notice, whatever made this flat surface sheared off the hard and soft rocks the same. It didn't matter whether it was soft rock or hard, it was the same. Now, erosion today erodes soft rocks faster than hard rocks. So hard rocks end up at ridges, and soft rocks are valleys or dips. But whatever did this just sheared it off. And I haven't been up there, but I'd be willing to bet that has rounded rocks on it, indicating that water was responsible for that. Now, the interesting thing is, what we observe today is that water does not form planation surfaces today. We don't observe them forming, except maybe in a local area along a river, if the river shifts in a flood and erodes a little ridge, forming a little tiny planation surface. That's all we observe today. We don't observe nature today forming planation surfaces. We observe it being destroyed. I'm going to get into this a little more. But I must first of all talk about, well, if you haven't got the hint yet, what I'm getting at is the flood is the only mechanism as it's moving out the continent to form planation surfaces. But when that's doing that, there was a lot of activity during the flood. You had mountains going up and valleys sinking. You had a lot of volcanism. So these planation surfaces were modified also. After they were formed, they got modified. They'd be modified by uplift and sinking so that you have it broken up and a piece go up like that and forms the top of a mountain. I'm going to show you some mountaintop planation surfaces soon. Also, further erosion by flood currents will whittle the size. All these planation surfaces I'm going to show you are probably 10,000 square miles in size at one time, but yet the currents of the flood kept dissecting them to the point where now they're just smaller remnants. Now, some of these planation surfaces are still huge, maybe 1,000 square miles, but they were probably a lot larger at one time. Also, a lot of volcanism has occurred and piled on top of these planation surfaces and disguised them. So those are the modifications. So despite this, you could still see them as you drive around in the western U.S. Now, in the territory where I live in Montana, Peter Kleberg and I have been studying planation, some special planation surfaces for about 10 years. In Montana and adjacent Saskatchewan and Alberta, there's generally 4 levels of planation surfaces, and the difference is about 2,000 feet. So we studied the highest planation surfaces. They form plateaus now. And these highest ones are right here. They're called the Cypress Hills and the Flaxville Plateaus, right in here. This is northeast Montana. These are plateaus in black. Look at the scale. That's in kilometers. That's 100 kilometers. That's equivalent to 60 miles. So this is a huge scale. These planation surfaces are really big. And here's a few just east of Glacier Park. Here's the Continental Divide right here. Now, the Cypress Hills I'm going to focus in on that. It's approximately 80 miles east-west and about 10 miles north-south. So it's 800 square miles. And it used to be solidly connected, but has been dissected by glacial fluvial rivers during the Ice Age. See, after the flood, there was an Ice Age. If you want to know more about that, I'll tell you all about it tomorrow, or I'll just tell you a little bit about it. I can't tell you all about it. But anyway, this was once a solid surface right here. And the interesting thing about the Cypress, here's some pictures of the Cypress Hills. Notice how flat that is. Well, I call it the Cypress Hills. It should be called the Cypress Planation Surface. Here's another one. Now, no one's going to get excited about going out to the... now, this is a resort areas in here. If you ever want to visit, it's some nice areas. No one's going to visit the Cypress Planation Surface. They'll visit the Cypress Hills. But this is an example of a dissection by glacial fluvial rivers. But notice how flat that is up there. Here's the eastern end of the Cypress Hills right here. It's flat, and it covered an area of about 800 square miles at one time. And when you drive up to it, that's what it looks like. It's about as flat as the plains of Kansas. I can't think of any place any flatter than the plains of Kansas. Hoping no one's from Kansas. But I love mountains. I'm from the Pacific Northwest, and when I drove through Kansas, I couldn't believe how flat it was. But this is just as flat. And then when you go to the edge of it, you're looking down 1,000 feet into the next planation surface, north into Alberta. Here's the flat planation surface, but look at what it's capped with. About 75 feet are rounded quartzite rocks that don't outcrop anywhere in the plains. They were eroded from the Rocky Mountains and brought out hundreds of miles from the Rocky Mountains and ended up on the top of the Cypress Hills, 2,500 feet above the rivers that go around it. And they're sticking up 75 feet of these things, 10 miles wide and about 80 miles long. Rounded quartzite rocks by water action. That's a huge amount of erosion of the Rockies. So you can see how rounded they are. And I might add something. A lot of them are iron stained. A lot of these quartzite rocks are iron stained. And you know, wherever I go, whether it's the top of the Wallowa Mountains, Puget Sound, we find a lot of them in the Portland, Vancouver area. You find them a lot of eastern Washington and even in central Oregon. They're iron stained. A lot of them are iron stained. So same in Saskatchewan, as if it was the same environment that caused the erosion. Also, you find another property of these quartzite rocks. They have what's called percussion marks on them. These are very hard rocks, but yet they have these semicircular cracks on them. Here's some more of them. This is more typical right here. You find hundreds of these things, indicating that whatever eroded them was just turbulent, bouncing, hitting each other with a lot of force to put these on there. Now, that's significant because we can figure out how fast the currents were going by these percussion marks. Now, here's what occurred. It was water that eroded from the Rocky Mountains, the quartzites. And in the process, it was so turbulent that the large rocks were sliding along the bottom. And the medium, the smaller rocks, were taken up into the current in turbulent flow and then come crashing down, banging against each other, forming those percussion marks. So what does that mean? Well, we can figure out the current speed because of the fall velocity versus the horizontal velocity. There's a relationship. And here's what we got. And I'm going to focus in on what's called a 6-inch bullet-shaped rock, 6 inches in diameter and bullet-shaped. We got from open channel flow equations in civil engineering, and these are minimums. We got minimum current depth of 180 feet and a minimum speed of 65 miles an hour. Well, the fastest flash floods on Earth go about 15 to 25 miles an hour, usually down steep slopes. Now, what are we talking about? We are talking about powerful evidence for the receding of the floodwaters off the continents and spreading the quartzite rocks hundreds of miles from their source. And then continuing to erode, leaving the Cypress Hills an erosional remnant 2,500 feet above the rivers that go around it. We're talking about powerful spreading of rocks and then powerful erosion afterwards. We summed it up in a publication, the International Conference on Creationism in Pittsburgh in 1998. Large rocks were transported 300 to 1,000 kilometers. Yes, 600 miles is about the furthest I would say they were transported over a low slope, not a steep slope, a low slope. Based on paleohydrological analysis, the rocks were transported in currents significantly faster and with greater discharges than modern flash floods. We conclude that our watery catastrophic process of regional extent very likely accounts for the gravel-capped planation surfaces. And here's kind of a way I envision it. This is a simplistic cartoon. During the flood, you had all this uplift occurring, whether it's granites or sedimentary rocks draped over the granites. And the flood waters were receding, and it sheared these things flat. And when it was ended, it ended up with a capping of rocks on the top. That's the big picture. Simple picture in cartoon style. That you see around where I live. Now, the interesting thing, you don't see them just in the Cypress Hills and other places. These are global. These features are global. Even on Antarctica, if you've ever seen any of the mountains sticking up out of the ice, some of them are flat top, sheared off. And I'll show you some pictures. These are the Beartooth Mountains in Montana. These are the highest mountains in Montana, 13,500 feet. They don't quite get up to Mount Rainier standard, but they're still very impressive. But look at that. That's the very top of the Beartooth. Look at how flat those surfaces are. That's granite. There's nothing in nature that is going to shear off granite flat. It's like a giant Paul Bunyan with a huge chainsaw went to the Teton Mountains and zipped off the Teton Mountains to flat. That's what it's how you can visualize it. There's a close-up of it. And by the way, they're at different altitudes because of tectonics. You know, where some parts went up higher and others sank down. There's a fault right in there. That's granite. Granite sheared flat. Now, nature doesn't do that, but the flood can do it. Now, another mountain range is close. This is the Northwest Wind River Mountains. There's a number of flat-top granite mountains in this vicinity. This one happens to be Square-Top Mountain. Also in the Wind River Mountains, in the northern, there's sedimentary rocks that are flat. And this is a limestone mountain called Gypsum Mountain. It's about 11,500 feet. It's the beds tilt to the west about 35, 40 degrees, and look at that, sheared off. But note that, it's rather pointed, so it's not quite as complicated. You have the Teton Mountains, which are very sharp looking, indicating no planation, but you go to the northern Tetons, Red Mountain and Mount Moran, they're sheared off flat. In fact, Red Mountain has rounded quartzites still left on it. The nearest source is central Idaho. I'm going to check that out this summer. Anyway, to sum it up, I'm going to go to Lester King again. And it's a little hard to understand this. I'm going to translate this as I go. Now, Lester King has studied the whole Earth as a geomorphologist from South Africa. And he says these planation surfaces are worldwide. And he generally says there's about 3 of them. In any one place, there's generally about 3 of them. And there's some debate over that. But in general, I'd say he's pretty close. He says a planation of extraordinary smoothness developed over enormous areas in all the continents. It's a global flood, not a local flood. These planation surfaces are on all continents. And I got files on each continent on these planation surfaces that I'll be publishing more on planation surfaces and other geomorphological aspects in the future. But anyway, I'm going to skip down. With emphasis upon its extreme planation, they are really flat. It appears particularly flat when viewed in cross-section as across the intervening valleys of successive cycles which commonly intersect it. From it, that is, all these planation surfaces, most of the world's present scenery has subsequently been developed. Now, on my computer, I wouldn't have a problem reading this. It must be that this is PowerPoint 203 and I got 202. But anyway, excuse me for the mix-up there. But anyway, he is saying that you have these flat planation surfaces all over the Earth. Powerful evidence for a global flood. So what should we expect from uniformitarian erosion, slow processes over millions of years? Well, the resistant sedimentary rocks, the hard layers, will get eroded less and they will stand up as ridges. The softer rocks, that's what you will erode, and the unconsolidated eroded debris will develop, will collect in the valley or be taken from rivers downstream and end up in the ocean. That's what you should predominantly see. And we do see a lot of that. I mean, we can explain that in the flood also, but that is what we commonly find all over the earth. The hard and soft